Yeah. Um, a motor and a generator can have slip rings. In a motor, it's just the IEB thing that they have decided they are going to do DC motors, because in a DC motor, you if you have normally what we use for a DC motor is we use a battery. And then because we have to have the split ring commutator, so that split ring commutator can change the direction of the current every 180 degrees to keep it turning. Otherwise it will go up, down, up, down. I really need to record this little video. We made one and you can literally see it flop back and forth, and it's so cute. But it makes you understand. And then as soon as you switch the current to an AC current, then actually it starts turning, but the wires starts to tangle. So if you don't have the split ring commutator, the motor can still work. Okay, so the split ring commutator doesn't tell you that it's a motor. If you change this into an AC source, the motor will then actually work better without the commutator. But if it doesn't have the commutator, the wires that are connected here that connects the circuit will start to get tangled. And that is why you then, for the motor, would also need split rings. So even if it's a motor, then you'll have the one side connected to one ring and you'll have the other side connected to one ring, so that the wires cannot get tangled. So you can have, and then it will be called an AC motor. So you can have an AC motor and an AC generator. The difference between the two is that the DC motor will need DC, and therefore it needs the commutator. The AC motor doesn't need the commutator because it doesn't need the current changes anyway, but the wires will get tangled and you need the two slip rings. So slip rings actually goes with AC. Whether it's a generator or a motor, it doesn't matter. When you see the slip rings, it goes with AC, because in an AC motor it means you don't have to change the current to keep the motor spinning. It will change anyway because AC gives you a changing current anyway. So this could be a motor, even though it has slip rings, but it will just be an AC motor. The reason why, and you must always go back to the definitions basically for generator and motor. The reason why this is a generator is because they tell you that there is a power source. Okay, so they tell you there's a power source because they told you that it's a generator. But here, to see that it's a generator, here must be some form. Oh, sorry, there's no power source. There must be some form of movement for it to be a generator. And by showing you that arrow there, they are showing you that it's moving. So here it's going to be mechanical energy converted into electrical energy. And that's how you know it's a generator. Not because it has slip rings. Sorry. And you must be very careful about those names. So yes, they do ask you what they are. So they just say what are the components. So they are slip rings, so you got that right. Please don't ever put the word split in there, because then they'll mark it wrong. You must say slip, and you must say rings, because there are two of them, where the split ring is only one, and you need to add the word commutator there. Okay, so be careful for that. It's not just that makes it a generator. No, you can't. They can ask you. The only thing they do, though, is they connect the circuit, whatever you have here, your appliance, your light bulb or whatever. They connect the external circuit with your armature or your loop, your internal circuit. So this is always called the external circuit, where the power is being used, and that's called the internal circuit there, where the power is being created. So what they do is they connect the internal with the external circuit without getting all these wires tangled up. And that's literally their only function. They don't have any other function. Where the split ring, that's why they ask the split ring commutator more often, because the split ring commutator changes the direction of the current. In a motor, it changes the direction of the current to keep the motor spinning in one direction. But in a generator, so I could take this away. It could still be a generator, and I can take these. I can take the split rings out. What am I doing? Sorry. I can take the split rings out, take them away, and it could still be a generator, and I could replace them with a commutator. So here, instead of them, I can have a split ring commutator. The one side connected there and that side connected there. And the wires won't get tangled. And it's still a generator, although it has a split ring commutator. But what then would happen is what a normal generator, what an AC generator would look like that it was before. If you turn it up, it gives you positive. If you turn it down, you give it negative. So it will give you an AC output. So this is for an AC generator. But if you put the split ring there, the split ring commutator there, what it does is, remember the split ring commutator's function stays the same. So for this 1/2 cycle, so if it's turning upwards, it will give you that 1/2 cycle. Then when it's turning downwards, the current wants to change, but the split ring changes it back into the other side. So it does that. And then you have the up cycle again, so it will be that. And then as soon as it's trying to come down here and change the current, the split ring changes the current again. Remember, that's its function. It changes the direction of the current every half a cycle or every 180 degrees. In a motor, it does it to keep the motor spinning in one direction. But in a generator, it actually does the same as rectification, because it changed this that was AC into this that is now DC. So when you see this in a generator, it is still a generator, but it is now a DC generator because it's going to give me DC. And that's the part that they say is not in the IEB, but it has actually been asked because it's a form of rectification. And so they can ask, how can you change the current into DC at the motor? And then you can say, replace the slip rings with a split ring commutator, and that will change the current for you so that you can get direct current out of it. I hope that doesn't confuse you. Does it make sense? Okay, great. So you can get an AC and a DC motor, and you can get an AC and a DC generator. In the IEB, they just decided that we're going to focus on a DC motor and an AC generator, but the others still exist. Okay, so the components you're fine with. Did I actually answer your question? Okay. Then they say, explain why current flows in the coil when it's rotated. So this is a newer paper. You can see the mark allocation is not 2 anymore. It's now 3 marks, because this is again that magic sentence that I talk about. So when they say the current flow, why is there a current flow when it is rotated? So now you have to go through those motions. So what are you going to say to me to get those 3 marks? Start by what they're saying in the question. So they say when it is rotated. So when it is rotated, can't spell. So the rotation, so that is basically the movement. So in other questions, it might not be rotation, but something must be moving. So the rotation or the movement will cause what we want. And remember, it's induction, so we're always going to go back to our equation, the Faraday's law of electromagnetic induction, and we're going to do the magic sentence. So the rotation will cause what for us? Exactly. So the rotation will cause a change in magnetic flux. That change in magnetic flux will cause? Perfect. EMF induced. And the EMF induced will cause current. Perfect. And that's how you get those 3 marks. Don't write too much. This is literally what we are looking for in those sentences, or in those explanations. You can put a few more words in if you really want to, but you don't have to. And also recognized symbols like this. The delta is always change in. So you're welcome to write that. You can write it exactly like that. And you can write EMF. So please, we want bullet form in physics because it's not a language. We like it when you use bullet form because it makes it easy to give you marks. Then they like these at the end, in which, oh no, this is not the actual, how can you increase the current. I'm going to just move it to the previous page. It did belong to this question, right? So now they're asking us in which direction will the current flow. Yeah, it did belong here. From X to Y. So now you have to use your slap rule or your Fleming's rule again. So what I would do for these ones, always focus on one side. Because if you're going to try to do it for both sides at the same time, it does cause confusion. So if we're looking at this and we focus on the one side only, so let's do this side here. What am I doing? We can't put a current yet because they're asking us for the current. Let's look at that pink side there. They're telling us though that it's turning clockwise, so that's going to go up that way. If it's going up that way, that's your fingers. So if you're doing the slap rule, you're going to take your fingers and you're going to point them in the direction of that pink arrow. Your palm is still going to slap south. Are you doing it? Okay. Where is your thumb pointing? Up. Yeah. So if you say up, are you meaning this way? Okay. So that would be the direction of the current. So the current would be flowing that way. Let's just prove it by doing the other side as well. So if we're doing this side here, now we know they told us that it's turning clockwise. So this one is going this way. So again, if you're greeting that, so your fingers goes down towards the bottom and your palm is still slapping south, which way is your thumb pointing now? Down towards us, yes. So do you get that? Okay, so now we just have to look where these Y's are coming from. So it's going there to Y and it's coming here from X. So this could be one of those questions where they make you circle, which I would do if it was me setting it. So you only have to write X to Y or Y to X. So that would be then X to Y. Happy with that one? Good. It must be positive to negative. So let me just see what I'm doing. You greeting the output going south. Which paper is this? Which year? Last year's paper. Okay, wait. Let's just do the Fleming's rule as well because I'm 100% sure that we're right. But if we're using the right hand with the FBI, the F is going out of the page. I'm just going to draw it again. So F is going out of the page. I also get upset because they don't post, even for my further physics paper, they didn't post a fixed memo. So I'm going to go have a look for you because I have my original one that we used to mark this paper. So I know there were a lot of changes made in this question, and I'm not sure that the IEB posted the final version because they didn't do it for my paper. But let's just double check. If we're using FBI, so this would be your thumb. So your thumb is going out of the page because that's F. B, oh, why am I getting the other way around now? Okay, so F is going up that way. B is going to the south, and I is going this way. Why is that happening? Okay, I'm just going to do the other side as well. Oh, I'm using my left hand. Remember for generator, if you're using FBI, you have to use your right hand. Okay, so let's use my right hand. So use your right hand. F is going up, like we had it before. So that one is going up there. So that's our F. And that is going to be your thumb, FBI. So your thumb is going up. B is your index finger that is pointing towards the south. Now I'm twisting my arm again. I hate this law. F up, B to the south, which is your index finger, and I still get the current going that way. Did you do it? Do you also still get the current going that way? Yeah, and if we do it for the other side, still same thing. It's turning down, so that's our F. FBI, F is going down. Middle finger pointing to the south. Yeah, no, so it's perfectly right. It's definitely going, they say, in the external circuit connected to X and Y. So it's going from X to Y. Yeah. I will double check that one for us with my original memo, but I'm 100% sure that we are right. So if that's the thing that was confusing you, then it's great because you did get it right. But it doesn't depend from where you start because they started it here. So it does go around that way. And if they're showing you the arrow this way, this side must be going up and this side must be going down. So don't let that confuse you. Is that okay? Okay. So yeah, don't stress about it. You did get it right. Okay, let's go back there. So I don't know if this was part of that question, but we can answer it for that question anyway. Yeah, it probably, no, but it doesn't matter. We can answer it because it could be something that could be in a question like this anyway. So it says state one way in which the magnitude of the current in the conducting loop can be increased. Okay, so now at least it's only one way and not three ways. So let's see how many we can see. So they say the magnitude of the current. So that is induction. And that means we are still using our Faraday's law. So EMF equals or directly proportional to N change in phi delta T. So how can you make the current? So if you make the EMF bigger, you are, because of Ohm's law, you are making the current bigger anyway. So if we can look at how we make the EMF bigger, we are making the current bigger. So what would you say for this one? We can say 3. Yeah, so decrease the time by making it faster, by turning it faster. Yes. So you can turn it faster. What else? Those are the two safe ones for this one, definitely. Increase the number of turns in that loop, yes. And then when it comes to this part, remember that part is BA. So I wouldn't talk about the area because the area needs to be constantly changing. So rather just focus on the B. So what would the B be? Increase the strength of the magnetic field. So basically use a stronger magnet. Just don't ever say use a bigger magnet because that doesn't matter. I have very, very large magnets in my class that are super weak. So it doesn't depend on how big the magnet is. So we mark that actually wrong. Okay, let's see the next one. Okay, this one caused a little bit of confusion. So we ended up marking quite a few things right, but it's just because of there were some students that saw that ammeter as a light bulb. So in the end, we marked it right, even if they said that the light bulb goes on. But yeah, it was quite interesting. It is a coil wrapped around a soft iron core suspended by a conducting wire so that it is able to move. And that was the part that confused people because they didn't realize that it can swing. They thought it could just move from the left to the right. Sorry, I'm just closing the door here for us. So they thought this whole thing can just move left and right, but actually what she wanted them to see was that this can swing up and then swing back down. I don't know if you, what would you think when you read it? Can it move or can it swing? Yeah, see, that's how I actually also answered it when I did the memo. So that's why we ended up marking. There were three different options that we marked correctly. So it says a coil wrapped around a soft iron core suspended by the light wire so that it's able to move. But it didn't say that the ammeter is stuck. So what we were saying, it should have been here hanging on a I don't know, on a retort stand or something, then they would have realized that. Some people did answer it like that though. So they say the north pole of the magnet is moved towards the coil shown in the diagram. So the north pole is moving this way. So before you even start thinking, what's going to happen here at X? Will be a north pole as well. Because of Lenz's law, it's going to oppose the change in flux. So the law you know. So the new magnetic field the new current or the current induced will flow in a direction to set up a new magnetic field to oppose the change in flux. So that part you are fine with. Then the question said, what observations, no, sorry, that's not there yet. What side would be the north pole? You saw that already. And then the question says, as the magnet moves toward the coil, what would you observe? And this is where there were quite a few options then. Because as you're moving it closer, and if this is able to move, what would you observe? If a north pole is being created here, what will the North Pole and the North Pole do with each other? They will repel. So what will happen to the coil? It will move back. When you say back, be careful because remember what the markers have and what you have in front of you is only the piece of paper. So back could mean that. It could mean into the page. It could mean all kinds of things. So answer according to your page when you do these questions. So just say it moves to the left of the page. Then you know they're gonna mark it right. So it's moving to the left of the page. What else would you observe? So that's what I also said. I said there would be a reading on the ammeter. So those two things you can definitely not better on meter. There will be a reading on the meter, yes. So I also said those two things. And then the next question said, what would you observe when the magnet stops moving towards the coil? So if the magnet is not moving anymore, if it's standing still, is there still a change in flux? No. So there would be different things that then was marked right according to what was marked right for the first one. So in the first one, if they said move to the left of the page, then if the magnet stops moving, then the coil will stop moving and the reading on the ammeter will go down. Is that what you would have said? Okay. So what the other option was, is if people did say that it's swinging, so if it's swinging up this way because of the magnet moving up and the magnet stops, then it will stop and it will start swinging back the other way. And if it then swings the other way and the coil is moving this way, then there's going to be actually a south pole created there, which means that the ammeter reading will then go in the opposite direction. So there were quite a few things that were marked right. But what you said is perfectly right. You can just say the ammeter reading will stop because there's no, oh, they didn't ask for an explanation, did they? Yeah, this was the 4-mark question. So then we had to look at what did they actually say in the previous question? Why was there a reading on the ammeter? And then what is the explanation? So this was the long question. And now you can use your magic sentence, because now you can say, okay, for your answer that you said, because you said that the magnet, if it was moving this way, so now it was moving this way, and it stopped moving. Now you need to, so the coil is now just stopped moving. So that would be your, so what would you observe when the magnet stops moving towards the coil? So the first thing that you would say is the coil will also stop moving. And now we need to explain that. So for your answer, if you said the coil will stop moving, then why do you think the coil will stop moving? So this is where you could default into magic sentence anymore. Because if the magnet is not moving, what don't you have anymore? Exactly. So there's no more change in magnetic flux through the coil. And if there's no more change in flux through the coil, then there can be no EMF, and there can be no current. But now here you would have to say there can be no current to create a magnetic field. To repel the coil from the magnet. So it's a little bit more than what you normally would have, because you now have to say, why is the coil actually stopping? And the coil is stopping because it's not getting repelled anymore. It's not getting repelled anymore because there's no more current to create that electromagnet. The reason why there's no more current is because there's no EMF. The reason why there's no EMF is because there's now no change in magnetic flux anymore. So it's kind of almost going backwards from magic sentence. Does that make sense to you? Okay. So be careful how you answer these questions, so that you just make sure that you get the order right in what happens, and then what happens, and then what happens. Then you'll always get them right. Okay. Was there another part to that question? So are you fine with this question 10? Did I miss anything there? Okay. What was the... Okay, so that one I copied again. Yeah, about this one. Oh, I see now people... this is the one people also had quite a few comments about. The magnet is dropped through the vertical coil. This is actually our prac that we do with our matrix. We drop the magnet through a coil, and then they see this pattern. Now, which of these, just by looking at them, which one would you say is rubbish? Yay, yes, because as it goes in, it will create a current in one direction to pull the magnet out, and as it goes out, it will try to pull the magnet back in. Yes, so absolutely. Now we have to look at what is happening. When will the EMF be the biggest? As it goes in or as it goes out? As it goes out, because it's speeding up, remember? And then we know that whole change in time at the bottom. And as it's falling, it's going faster. So the time is decreasing and the EMF is increasing. So that means it kind of by default gave us the right answer already. because it needs to have a bigger EMF as it's exiting than when it's entering. So this one has a bigger one going in, smaller one going out. So that's wrong. This one, same in, same out. So that's wrong. So the answer is C. Did the memo not say C? Okay. So always just remember as it's falling down, oh, gravity, I'm seeing what you're saying. Because of it being pulled out, did you choose B? Okay, I can see that happening because what people do think is that because as it's coming in, you are right that it's going to form a north pole there, so it's going to try and repel this back, and it's also going to pull it back in when it's falling out. It's also going to pull it back in. But for these types of questions, please remember that gravitational force will always wins. So your gravitational force is going to be stronger. It has to be an insanely strong magnet for it to slow it down so much that the gravitational force is not going to actually win and pull it down faster. Is that what you were thinking? Yeah, it's actually first time I'm thinking about it like that because I've done it so much and I know it just goes faster, faster, faster. But if you haven't seen this in real life, I can understand that you're doing that because then it's slow. The magnetic field is slowing it down. The magnetic field slows it down compared to something that has no magnetic field. It's a very nice experiment we also do. We take a plastic pipe, so we throw the magnet through a plastic pipe, and then we throw the magnet through a copper pipe. So in the plastic pipe, it falls at G, so 9,8 falls and it comes out, and you can time it. And as soon as you throw it through the copper pipe, it takes much longer to fall out, but it is still accelerating. It's not going to go at a constant speed or anything. It's still going faster because the gravity is still making it accelerate. It just has it only has a downward force, where here it has a downward force and an upward force, but the downward force is still winning, so it's still accelerating downwards. This could actually be a nice Newton question. If we really want to be mean, we can put Newton in the electrodynamics question. I don't think I'll ever do that though. Does it make sense though? Okay. Was this on its own? Yeah. So let's see. Headlamp connected to the diodes. Okay, so we're going to follow the path again. Oh, wait, let me just make it smaller. It's giving you an axis. Great. It's giving you the current. Let's just see where they want. On the axis, sketch the graph of the reading on the ammeter versus time when the wheel is spinning to show the current through the headlamp. Okay, so here is the headlamp. So this is what we are interested in. And they have an ammeter there. So they do tell us though that it's an AC generator. So what they could have just done here is give you one of those squigglies. As soon as it's an AC generator, it means it's one of those squiggly sources. So you're going to do that whole maze walking thing, is what I call it. So we're going to make this positive, and we're going to make this negative, and we're going to see where we go to get that first. It doesn't matter where you start. It really doesn't matter because it's a current output. So you don't have to worry about going down first or going up first. It really doesn't matter because they didn't give you a flux graph. So we're going to go in and here. Can we go this way? No, because that block wall there is stopping us. So when we walk down, we can't go that way, so we have to walk this way. So that one's cancelled out. Here again, can't go there, wall blocking us. So we forced to go this way. Whenever you see that little squiggly, it means the one wire is going over the other wire. So here we're going over the other wire and we're going down through our light bulb. So the light bulb is experiencing a current in this direction. Going back, going back. Here, please remember it cannot go back to positive. So it has to go back this way to the negative. Then, oh, is this where there's, oh, then here it also can't go back there. So it's going underneath that wire and back to the negative. So one of them will always be a longer path. When the load is not here in the middle, the one path will always be a longer path than the other. So that would be this is going to be our long path, and that will give us that first little loop there of our wheel, of our spinning. Then we can swap out currents. So now we're going to make this one positive, this one negative. So we're starting on this side. From positive, we're going this way. We're going to go under that wire. And when we get here, again, that blocks us. Can you see that wall there? Blocking me there, so I can't go there. So I'm going up, 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 up. Can't go there because I'm getting stuck there with that wall. So I'm coming back here, going over that wire again, coming down here, and there I go. In my loop, I'm getting a downward current again, going this way, going this way, going this way. Here, I cannot go back. Can't go back because that's going to go back to positive. So this time I'm going this way. Can't go back to positive. So that means I'm going up here and up there, ending at my negative. Always start at your positive. Make sure that you end at your negative. And because my light bulb sees a, when I say see, please remember they still don't see. The light bulb experiences a current in that downward direction, and it will give you that. Can you see the paths? What was confusing you about this one? Okay, but it's even with, you know what, if this is at the end of the paper and you see 4 diodes, this is 99% of the time what it's going to look like. Because the 4 diodes, and especially if they ask you to draw a graph, if they're giving you 4 diodes, they give you, remember this is called a bridge rectifier. When they're giving you a bridge rectifier with the 4 diodes and not just one, the chances are 90, and they're asking you for a graph, it means there is a graph. It means that one of these paths are not going to stop it. But you still need to check, because what they meanly sometimes do is that one of these paths don't work because a diode is connected in the wrong way. So then maybe the pink or maybe the blue one would not work. But I have only seen that in A-level papers. I've never seen that in an IEP paper that they do that. So if you see 4, it's probably going to be full wave rectification, and you're going to get that blue, pink, and then blue again. All you need to read about carefully is how many loops do they want. They said on the axis given, sketch the graph of the reading on the ammeter versus time when the wheel is spinning to show the current through the headlamp as the wheel spins. So they didn't tell you how many rotations. So if you just did 1 or if you did 2, that would be perfectly fine, and they will all be the same size, and they will just carry on like that. Was there a, I can't remember where this is from, but if there was a follow-up question and say, if you replace the bridge rectifier with a single diode, they could ask you that. And then what you would do is you would just make these middle ones disappear, either the first ones or the last ones disappear, the pink or the blue, and that would be giving you, as this would what it would be it would look like as it was if it was a single diode. Then you get half wave rectification. Okay. All right. Have you seen now when you're looking at past papers how many of these little pictures you see? So I'm glad we did quite a few yesterday. Oh, when was it? Yeah. You have a uniform magnetic field shown and you have your loop of wire. In relation to your page, what is the direction of the uniform magnetic field shown? Yeah, I don't know why that was 2 marks. What is the direction? Yeah, I really do not know why we made that 2 marks, but yes. Into the page. Describe 2 ways in which you can generate. So can you see it's almost exactly the same as that one we had yesterday. Describe 2 ways in which you could generate a current in the loop using the uniform magnetic field shown. So she's being very specific now about telling you that you can't change the equipment. So when you do a question like this and they don't tell you that you are allowed to use different equipment, please don't. Use the stuff that's given in the question. She was quite pedantic. I mean, yeah, that she was deliberate about it and said the magnetic field shown. Okay, and it's this loop, the wire loop. So it's this wire loop. You can't change the wire loop. So how can you make a current flow in that wire? Yep. So you can move it. Okay, wait, careful. These things do get a bit painful because now, let me show you. There's our loop. So if I say I'm moving the loop towards or away, I'm doing it. I'm moving the loop towards and away. Is there going to be any current? No. Yesterday's one was a magnet. So, okay, so I'm going to draw a magnet on the other side. So if it was a magnet, remember the magnet has the field lines coming out. So if I'm moving that loop towards my magnet, come now. There we go. If I'm moving my loop towards the magnet, because the density is not constant of that magnet, if I move it towards the magnet and away from the magnet, yes, there will be a current induced. But if I'm moving it here, there's no field lines here. So you cannot just say, move it towards the field or away from the field. What must you say? There we go. Moving it into the field or moving it out of the field. You could have even said move it from the one side across the field to the other side. That would also be, as long as you keep it moving, you could say that, yes. So that would be, remember, that would be one way. You cannot say move it into the field as one way and then moving it out of the field as another way. That is seen as one. Into the field and out of the field is seen as one way in which you can generate a current, not 2 ways. So what else can you do with this loop? You're not allowed to change its area because they say this loop. You can rotate it, but again, like when it was here and you rotate that loop, don't know if it's going to let me do it. If I take my loop and I do this and I rotate it, now the field lines are lots, more, less and more, less and more. If it was the magnet, but if I do it less and more here, and I say less and more, and I'm rotating it, one side, other side, one side, other side, am I changing the field lines? So again, you must be very specific. I need to do it here. I need to do it here on top of that magnetic field. If I do it now, can you see if I rotate it? I'm spinning it, spinning it, spinning it. Now it's going to be in the vertical, so it's horizontal position. So lots of field lines. Now I'm spinning it, spinning it, spinning it until it's in the vertical position. No more field lines. Flux is zero. Taking it to the other side, which I can't do, but it doesn't matter. Taking it to the other side, spinning, spinning, spinning. Now it's in a horizontal position anymore. Do I have a change in my flux now? Yes. So when you say rotate, you have to say rotate it while it's in the magnetic field. Because if you're just going to say rotate, you could be meaning that it's rotating here, which makes no change in the magnetic flux. It has to be rotating here, otherwise now there is a change in magnetic flux. Okay, so be careful about these. I know it sounds a bit as if we're a pain, but some people who rote learn these things and don't understand them. So moving in and out, perfectly fine. Moving into and out of the field must be the one. Or moving it across the field, that would also be fine. Or you have to say rotate the coil. But you cannot say rotate the coil. Did they call it a coil or a loop? What did they call it? A loop. Loop in field. And you could also not say anything about the windings because they said in the wire loop. So you're not allowed to change the wire loop. Well, you did this one right. I hope so too. Think you will. And here's another one. At least when the exam comes and you see one of these, you're going to kind of feel familiar, right? Because you've seen so many of them now. I really will be upset if you don't get one of them in your exam now. Okay, so let's see what's happening here. Two copper rings of different sizes are placed in magnetic fields, P and Q. In which of the following combinations is the magnetic flux and the magnetic flux density greater? Choose the option. So they're actually just testing the definitions. So the magnetic flux density, remember that's how close the lines are to each other. And they didn't say in the loop. They say in which of the following combinations is the magnetic flux and the magnetic flux density greater? They didn't talk about the loops at all, and that might have confused people. Because if you look at the density here, you're looking at how close these crosses are to each other. So that's how close they are. Where here, this is how close they are. So where are they the closest? So the magnetic flux density, remember, density is how close they are. So that means when we're looking at density, it's B. But then they want to know magnetic flux. What is magnetic flux? The amount of field lines. And they didn't say through the coil, which I now think is a bit of a problem with this question. Two copper rings, different sizes, are placed. They say, in which of the following combination, magnetic flux and the magnetic flux density greater? They should have said magnetic flux and magnetic flux density in the coil, but they didn't. So if it's not in the coil, which of P and Q have the most lines? P still has the most lines, yes. So that would mean that the answer then should have been A. Was it A? Yeah, see what they're doing this exact thing what I've just added. So the wording in the question is a little bit squonky because they had to, and so when they say magnetic flux, we generally assume that they are talking about the area, and but it shouldn't be assumed. We should say it. So if we're looking at the area of this coil here. This one has more field lines going in that area as that one. So this one has our 9 lines, that one has 4 lines. So if we're looking at the magnetic flux in the coil, and this is what the question is assuming. So that they should have said. So if we answer the question like what we would expect they're assuming, then the answer would be D, because greater magnetic flux would be in Q, because there are more field lines in Q. This was last year. Let me check. Oh, 2021. Yeah. And it's May. Okay, that makes a lot of sense, because in the May paper, there's not that many people that see the question that can comment. It's definitely a glitch in the question there. They should have told you in the coil. It would probably be one of those where they discussed it in marking and gave both, and both those options were marked correctly. Is that where you got confused? Okay, yeah. So if you looked at the magnetic flux as the total number of field lines, you actually did the right thing, because they should have told you that it's in the coil. Those words are missing. Okay. So if you do see a question like this in a longer question section, just make sure that you refer to the field through the coil, or in that area passing through the coil, or something like that, because we will look at that definitely in the final. We will look at that. Hopefully, I don't think it will be the question I mark anymore, but I have it copied it twice on top of each other. Okay, let's see what we have here. How would you know this is a generator if they didn't tell you that it is a generator? Now they're moving it, so it's mechanical energy into electrical energy. Can you see there's not even splittering or slipping here? So that's why you couldn't use those two to differentiate between the two. Alright, so the hand-operated generator is shown. The turning of the handle causes the metal disc to rotate. The handle is joined to an axis again. Brush X. So brushes, remember, is something that is stationary, but normally the wire there can roll over it. So brushes is things where the circuit is mobile. So that can move around it, this can move around it. So brushes always helps with wires not getting tangled. So as soon as you see the brush, then you know the wires won't get tangled. The turning of the handle, okay. So brush X touches the metal axis, and brush Y touches the rim of the disc. Okay. If the metal disc is rotated uniformly in the direction as shown, which statement about the current in the globe will be correct? Okay, so it is moving. So will there be a current in the loop? Okay, so now we just need to how is it moving though? It's turning this way, so it's moving that way. It's not, or is it moving this way? It's a bit difficult to see here. Where is this question from? Okay, anyway. So let's just assume. So see, these are those type of three-dimensional questions where I think a lot of people are going to get it wrong because they're not seeing what they're actually trying to show us. Okay, there's the globe. So let's just assume the direction as they're giving it to us and the angle. So this one is moving upwards. So if that is moving upwards there, the magnetic field is going from north to south. If that one's moving upwards and we're slapping south, Yo. They're saying rotated in the direction as shown. So this thing is moving this way. I don't know. I want no current to flow. What was the answer? Okay, can I tell you why I want no current to flow? Because if the way I'm seeing it is that this loop is in the magnetic field, and if this is just a metal ring, and that metal ring is just turning, 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 and that flux is that flux going from north to south. Is that flux going to change if this thing is just spinning round and round and round in that same position that it is? No, and that's how I'm seeing it. But I'm obviously seeing it not in the right way. But then it feels to me as if these arrows are not right. Because for me, then, for anything to start happening, this should rotate in the magnetic field, which means this one should be turning this way, and this side should be turning this way. Are you seeing what I'm seeing? Okay. So if that is what they're trying to show us, then they should have made those arrows a little bit more bendy, which means that this one is going that way and this one's going this way. So then it could work, because then we can say, okay, the force is going that way. I am So it's going basically going into the page, being turned into the page. The force is going that way. I'm slapping south, and then the current in that, if that is what they try to show, then the current would be going this way. Are you getting that when you're using your hand rule? So do it with me. So you're greeting the blue line into the page. So you putting your fingers into the page as if it's rotated into the page and then out of the page. And then you slapping south. So my thumb then is pointing down to the bottom. Are you getting that? Okay. Okay, so then it works. So if you are then looking at this side is coming out of the page towards us. So you're greeting the current towards you. You greet, or not the current, the motion. So that blue arrow is then the force. So it's being pulled, it's being rotated out of the page, and you're slapping south, which gives me a current that flows in that loop upwards. So the current for me that I get then is that the current does this. Do you get that as well? Okay, which would mean that the current in this loop is then kind of going clockwise. So if we're doing that, let's just see where their x and y. So here's their x, then it is going from x upwards here to y, which would be then that the current flows x to y. But that's the thing with these things, with the 3 dimensions. Because that arrow just points up, it could be that this one is coming out of the page towards us. Can you see what I'm saying? So this could be coming out of the page towards us, so yeah, this way, and this one could be going into the page. Even if the arrows are like that, up arrow could be meaning out of the page that way, and this could be meaning into the page, oh, that way. So it very much depends on how you see this diagram, and because it wasn't drawn nicely as 3-dimensional, and these arrows are not bendy, I would say this is a very unfair question. They can't really give you this, because if it is just being rotated like this, I'm actually going to go look at the comments for this paper. If it was a November paper, I'll have the comments. Otherwise, I'll ask. Because if it's just rotated like this, there's no change in field lines, and then the answer should be A. If this was a May paper, please tell me that I can ask them. Was this an IEB paper? It's probably a May paper. I haven't seen this thing. Because I never do the May marking, because I'm marking further physics when they're marking when they're marking the normal IEB papers. So chances are it's this one, the same one as this 1.10, 1.9. It's probably from the same paper. Yeah, okay, that makes sense. I'll ask because there's lots wrong for me with this question. I'll ask her. I'll ask the examiner because I wasn't there. Yeah, but there's for me that this question doesn't work out at all. But do you understand what I'm saying? Okay, it has to be rotated like this, like flopping in and out of the page. It can't be just a ring, like a bicycle. If this was like a bicycle ring, just turning around like that, there's no change in flux. There can be no current, and that's what I see from these arrows. Okay. Bird oh, I copied these again for some reason. Okay, let's look at this one. We haven't done this one. Okay, loop of wire. Oh, they're giving you the side view and the top view. Okay. Side view, top view, direction of the current in the loop is indicated. The loop of wire experiences a force. Using the side view, will the loop rotate clockwise or anti-clockwise? So it is experiencing a force, so you know it is a generator. Oh no, is it? Okay, so they didn't say we causing the force, it's experiencing a force. So because they say the direction of the current in the loop is indicated, we're assuming that it's current going into motion. So it's electrical energy into mechanical energy. So it's like the motor effect that we are going to use. Will the loop rotate clockwise or anti-clockwise? So if the current goes this way, I'm just going to do one side again. So if the current is going this way and it's the motor effect, you're greeting the current. So your palm, your fingers goes up to the top of the page for that pink line. You're slapping south, and I get that this side here is going into the page. Do you get that? Okay, so that means that side's going into the page, and if we are looking at it here, that would mean that this one here let's go. Okay, now they don't tell us we're starting, but we can do this one on our own just now as well. But I get into the page there, so it's this way. See again, those arrows are very, if they're not in 3 dimensions, very hard for everyone to see it the same way. So if I'm doing that, I'm meaning into the page, but someone might see that as out of the page. So it's tricky. Now if we go to the other side, this one's going this way, so our fingers is going down, we're slapping south, and it's out of the page. So you will always get opposite. So if that one's going into the page, this one's coming out of the page. So what we are getting then, if we look at that one and we're looking at from the bottom, I would say that is clockwise. But let's look at this one. So they say using the side view, will the loop go clockwise or anti-clockwise? So let's use this wire there. It's actually much easier with this one. I didn't see that they want us to use the side view. If we're using the side view, there we have the current. So we're greeting the current. What is the cross? Into the page. So we're sticking our fingers into, okay, that's much easier. Sticking our fingers into the page. We're slapping south. So I get that this one is moving down. Do you get that? Okay, let's look at the other side. The other side is coming out of the page. You never have to do both sides. I just do it to check. So that means you greeting yourself. Your fingers comes towards your face, slapping south, and I get that wire there is being pushed up. Okay, so if this one's going up and this one's going down, we're getting the same answer, which is clockwise. Were you happy with that part? Okay. Then they say using the side view diagram, will the equilibrium position of the coil be vertical or horizontal? Now, what they mean by equilibrium position was a bit of a tricky situation, because is the equilibrium position when it's zero, when the flux is zero, or is it not? So if we are saying that the equilibrium position is so if you're going like this, if you're seeing the loop, if we are saying that the equilibrium position is where the flux is zero, and the question wasn't clear about that. When the flux is zero, they didn't say if it's flux zero or EMF zero. So we're just assuming that they want the flux to be zero. So if the flux is zero, then the equilibrium positions here, that is zero. So if you get a question like that, I would actually draw a rough little diagram and tell them what you are understanding under when they say equilibrium. So that's equilibrium, that's equilibrium, that's equilibrium, that's equilibrium. Because for a normal wave, that would be the equilibrium positions. And if we are looking at the equilibrium position, that would mean is it in the horizontal or vertical position? What would you say? Horizontal position. Is that